We've been talking about fluids on structures, and we've kind of alluded to it already, that the pressures that act on structures, if you take a bucket of water and put it underwater, then the pressure acting on the top of that bucket is less than that acting on the bottom, but it's neutrally buoyant, except for the weight of the bucket. If you turn it upside down, it would be neutrally buoyant. Oops. Actually, nice music. But if you take the water out of it, then the force acting on the underside is larger than the force acting on the top, and it becomes buoyant. And so buoyancy is just a consequence of forces acting on structures. And so it'll continue kind of from what we've been talking about. So you can look at play submarines. I guess that's what this is. There's a famous example of some guy in Denmark who made his own submarine and took a reporter out on it and killed her and dumped her body in the water. I'm not sure why I'm bringing that up, but it was a kind of bizarre thing of the last couple of years. This is interesting as well. So this is quite spectacular. An emergency breach, I guess, to get yourself out from under the water as quickly as possible. And so it's an emergency maneuver, but quite spectacular. There's no real scale on the submarine, but you know it's a big behemoth, the size of a whale, I guess hundreds of feet long. And I guess the consequences of those kinds of things. I remember there was one of those, the navies will do that as a maneuver, I suppose. And certainly a consequence of one of those emergency breaches was coming up under a boat. And one of those ships was the Ahimemaru, which collided with the USS Greenville submarine somewhere near Hawaii, and sunk the boat. The boat was a training vessel for Japanese apprentice fishermen, and so sunk the boat tragically. So again, buoyancy. When was this? 2013, so 10 years ago. You'd have been 12 or 10 or whatever. And so the Costa Concordia was a cruise ship whose captain wanted to show off to some people on a nearby island by sailing close. And so while he dined at the high table with the dignitaries on board, they came just a little bit too close to the island and ripped a big hole in the bottom of the boat. And we're very, very, very lucky that when it came to rest and then ultimately would have capsized, it capsized landward and was resting on the shelf just offshore the island. And so the interesting thing with this is what was done to be able to salvage it. Sitting there, maybe 40 people died, but certainly you could imagine that if it had capsized and capsized quickly, if it had gone the other way, then it would have been a much bigger toll. And so here you see the mechanisms to right it, putting on an appendage, maybe putting weight on that, pulling down on this to be able to right it, and then attach, if there was weight in this, and blowing out the water, I guess it is, putting water in it to be able to pull it down. Once it's righted, you attach one to the other side, and then I guess you evacuate these containers of water, and Bob's your uncle, it floats. So buoyancy is what we'll talk about. Don't know what that was been. That's from a previous year. And of course, the other submarine story is the Glomar Explorer. You probably know the name Roger Ballard? Richard Ballard? Ballard? Is it written there? So this was ostensibly a deep-sea mining ship to be able to mine, to grab nodules, manganese nodules and whatever concentrated hydrothermal deposits there are on the seabed near deep-sea vents. And they took it to mining exhibitions to get finance and venture capital for it. But actually it was all a big ruse by the CIA to be able to take it out to the middle of the Pacific, park it over a Russian submarine which had tragically sunk underwater with probably all lives lost, and then try and recover that submarine. And they did get some of the submarine up, I think it broke just as it came up. It was actually had an open bay in the bottom so that the cranes could go down and grab the submarine from it. So plenty of movies about that, but it's kind of an interesting plot. So that's the topical interest for, I guess, what we'll talk about today. So, well, what do we have to chat about? So this is the last period that we'll talk about statics, fluid statics. Actually, our 4.1 classes will be online next week, but 4.1 is the very last act of fluid statics, which is kind of a misnomer because it's accelerating fluid. You remember we looked at the bus with the water trap between the glass sheets. When you accelerate, it piles up at the back. When you decelerate, it piles up at the front. And so static means that the fluid isn't circulating or flowing, it's just moving within a container. And so that's the last part of what we'll talk about in the first part of this class. And that brings us up to the material on the first midterm. I set groups yesterday, not on Wednesday, so you'll find yourself in presentation groups. Your usual email that comes out tonight at midnight will have instructions on how to find out what your groups are. So I think the schedule is within the next 2 weeks by Wednesday of week 5 to meet with your group, and by week 7, the 2 weeks after that, to come up with a title for presentation. So put that on your calendar as well. So you'll get a reminder. If you're not getting these reminders on Canvas, you must be skilled Canvasites by now, so you must have your email announcements forwarded to you, I would think. But if you are missing those announcements, then just set up Canvas to do that. So that's kind of where we are. So we'll finish off statics today. So first week, fluid properties, density, viscosity, compressibility. Second week, fluid pressures at a point, which of course rely on the magnitudes of those masses and changes in masses with pressures and integrating those. And this week has been looking at fluid pressures at a point and then integrating them first over planar surfaces, which we dealt with last time. And just to recap from what we talked about last time, I'll go back to the very nice figure that I think I was very proud of, but you'll see it multiple times in these notes. And that is that for these plane surfaces, and it's really been incompressible fluids, it's what we talked IBLE, right? These equations always hold. And that is that the force acting perpendicular to that surface is always equal to the average pressure on the surface, which is the first two terms here. So you can think about this as being the pressure at the top of this plate, this being the pressure at the bottom. It's a linear distribution. It's flat distribution if the plate's horizontal. It's the steepest distribution if the plate is vertical. But regardless, because it's a straight line, the middle point here must be the average pressure. So this would be P average. This would be P average, which is the first two terms, which is just the depth of this location below the surface multiplied by the unit weight. The appropriate point to choose is always the centroid of the plate, which, as we've explained multiple times, is kind of the balance point of that plate, the center of the structure. If you draw a line for a rectangle from top left to top right to bottom left, etc. But the location where it acts is always given by the center of pressure. And you get the center of pressure by measuring the slope distance down from where this plate would intersect the surface, the x-axis and the y-axis. And it's given by the slope distance of the centroid below that intersection, which is y sub c, and some small increment in addition to that, which we've called delta yc or delta yr. And so that's what this term here is. And it's a standard result in that it's the slope distance, the area of the plate in yellow here, and the second moment of area about the centroid. And this is just a standard result, which if you've looked at some of the tests you would be given, and it conforms to these, which are in the book if you have it, or and actually the edition that I have is not the 7th edition that you can find for free, it's the 6th edition, but they're all very similar. And so we did something with this last time. Happens that for a circle, the second moment of area about the centroid is the same for both of these terms. For a plate, which we also used as well, it's this magnitude here, and its standard result is a 1/12 of the width of the plate times the depth cubed in the plate. And so those are standard results. And it depends on the shape of the plate, not its attitude within the fluid, just the shape of the plate. The centroid of the plate is given by this point here, and it varies for different structures. We'll use this one today to do some examples to finish off what we're doing by looking at. So what we'll do today is move on from planar surfaces to curved surfaces, and then to talk about buoyancy as well. Okay. So that's kind of a summary of what we did last time. So some examples. And so we'll move, it's kind of a contrived example, but it serves to make the point of talking about behavior for curved surfaces. And so the question here is, what are the forces acting on this segment of the pipe if you cut it in half? It's kind of contrived because why would you cut it in half? Why are you interested? But let's assume that we do want to know that. So for curved surfaces, I suppose you could think about this. We know that the pressures acting on a surface always act perpendicular to it. The resultant force is always perpendicular to the plane. And so if you think about what this pressure distribution would look like, you could probably, I can't draw it very well, but it wants to draw a straight line, and I don't want it. So if you drew a whole bunch of the pressure distribution on the surface, it would be a whole bunch of little arrows perpendicular, and the arrow here would be of 0 length, right, because it's at the surface. And so if you wanted to calculate what these forces are, you could make a free body diagram that was just this skin of the pipe, like we did for the rectangular opening gate that we talked about last time, just to remind you. We did an example with this opening gate, right? You have forces acting on this gate, you have pressure acting on this side, you have vertical pressure acting on this, and we can take moments around here for this force acting horizontally and this force acting vertically. So we could also, just as we did for this, we kind of drew a free body diagram that just enveloped this gate alone and nothing else, and drew the forces, the pressures acting on it. We could do that for this section as well, but that's not very, very convenient for us to do it. So what we'll do instead is we'll make a free body that cuts this in half, right here, and isolates this free body, which is ABCA. ABCA. And we can look at the force that acts on this, and it has to be reacted against by this, because we know that the sum of forces in the x direction have to be equal to 0, as do the sum of forces in the y direction equals 0, as do the sum of moments equals 0 for these systems to be static. And we can figure out exactly what the force is that we're acting on this. So the forces acting here would look like this. A pressure distribution like this. And so we can calculate F1 is going to be equal to unit weight times the height of the centroid times the area. And so this would be the unit weight. What's the height of the centroid? Well, you can think of this as being a plane. The plane would look like this. And if I even complicate matters by doing my x, obviously the height of the centroid is half height. So this would be equal to 3 over 2 feet, because it's 3 feet tall. And the area would be 3 feet times a 1 foot length. And so this would be the force acting horizontally. And you have that here. And so F1 and FH would be the same. They have to balance. We could do the pressure inside here, but we don't. We have no pressure acting on here. So the force acting downwards is just the weight. So the weight is equal to the mass times G, which is equal to the volume times the density times G, which is equal to pi r squared, I guess, over 4. You have it here. Multiplied by the density of water, multiplied by acceleration due to gravity. I guess these are English units, so that kind of gets screwed up. And so it's the volume is pi r squared over 4 multiplied by 1 foot into the page. And so the weight ends up being this, which is the same as the vertical force acting upwards. The horizontal force is this. If you go through the same calculation that we just did, this, I guess, is the unit weight. So did I write that? Yeah. Rho g is correct. This is also rho g. I guess in English units it's just 62.4 pounds per cubic foot. If we wanted to, the resultant would be obtained by looking at the sum of those. So we have the vector sum of those. So we have horizontal force, bless you. We have the vertical force, and the resultant of those, FR, is just the square of those. So this is just Pythagoras, right? And so the magnitude of those would be equal to FR. And you can calculate that. It's probably calculated for you. And of course, you can calculate the angle at which it acts because you know the magnitude of FR, absolutely. You know the lengths, each of these individually. So you can just work it out as a sine, if you wish, or a cosine. And so that's that. I guess the other quirk is that if you wanted to, from what we said about the, you can rationalize the line of action of those forces. If you think about the diagram I tried to draw before, that gives you the pressure distribution. So if you have all these individual pressures acting perpendicular to this surface, they all, by definition, pass through this point. And so if you can intuit, I guess, that if by definition they all go through this point, the resultant would also go through this point. And it does. But you can also show that is the case, I guess, because you know, if I remove this, you know that you have FV acting here, and you know that you have FH acting here. And so what you could do is you could take moments about this point, and you see that this 1.27 feet is equivalent to the location of the centroid. So the balance point for this is the centroid of this is the balance point. If you put it on your finger, it would balance on it. And so that by definition, the weight of this acts through the centroid, W. And this happens to be 3r over 3 pi, a standard result, distant from this location here. So 4r over 3 pi must be this 1.27 feet that you see here, which is the location at which this acts. And so what you could do is you could write FV times LV clockwise, counterclockwise, minus FH LH equals 0. And you'd find out that from the magnitudes of these, I guess what are you solving for in this case? You'd find out that since the moments around here are 0, the fact is that the resultant has to act directly through this point somehow. So you'd find it. So you have magnitudes for this, you have magnitude for this, you have magnitude for this, you have a magnitude for this. You don't necessarily need to assume this, but if you did that calculation, you'd find out that they sum to 0 because it acts through here. And so from that reason, you know that the points would act through there. Kind of a novelty more than anything else. So the other thing you could do is you could look at forces acting on where there's not the free surface there. And again, you can do a free body diagram. And in this case, the easiest free body diagram would be to take this A, B, C as a separate component. If you looked at the magnitudes of the pressures acting on this, they would look something like this. Right? And if you looked at the pressures acting on here, well, this amount here would be the vertical pressure acting downwards. And of course, this magnitude here is exactly the same as this magnitude here. And you could use those distributions to figure out what those forces are, or you could just use what we've done already to be able to figure out those forces. So one way to do it would be to calculate the pressure acting on this plate. So F1 would be equal to what? It would be equal to HA times the unit weight, which would be the average pressure. This term here, multiplied by the area AB. So this area. So that is the pressure acting here. Pressure acting horizontally would be F2. F2 is equal to the depth of the centroid. This is not HC, is it? This would be the depth HC2 times unit weight times area. And so this, the depth of the centroid would be HA plus half of this height. So, and you see how to do that. And then you can resolve forces. So you have a pressure acting on the top, which is this. You have a pressure acting on the side, which is this. You have a weight of the structure, the fluid that's in this enclosure, which is going to be W equals volume times unit weight equals pi r squared over 4 times 1 meter times, if it's water, 9.81 kilonewtons per meter squared. It's getting crowded. And then you just resolve these for the other magnitudes. And so it's just a matter of being creative about these things. And so the reasons that these curved surfaces are kind of curious is that, and the reason that you see sluice gates often arranged so that they rotate up or down is this idea of a tainter gate. And that is that because the pressures acting on the outside of this all act perpendicular to this arc, if it's a circle, has a fulcrum here, and so the pressures all act directly through this fulcrum. So there's no bending moments that are applied to the plate. And so you can make a gate which is really quite light and available. So the deal with these things that we've just looked at, there's one other utilitarian thing that I have, if I can find it. I think it's this, yeah. So this is worth, so it kind of gets maybe a bit confusing because we've done these things so differently. But this is perhaps worthwhile looking at or even taking a photograph of. It's not in your notes, but and I don't want to draw it out. But it's just, these are all equivalent ways of solving the same problem. And it's the problem that we did last time, which is this gate that has a hinge on it. You have a pressure acting on the side, and you have a pressure acting on the base. The question is, what is the force P that you have to apply to be able to keep it shut? And so you can skin that cat three ways if you want to skin that cat. This is the way we did it. We calculated the pressure. We drew a free body just around the gate, and we calculated the pressure acting on the inside of this, which was a linear distribution of pressure. It's not zero at the top because it has a certain height. And of course, we can calculate this by just using this equation here, right? We just need to know exactly where the centroid is on this. And the centroid would be halfway down this, the depth that's halfway down this, depth from the surface, which is halfway down this. And we can do the rest of the calculations. So this is the way we did it. We got a force horizontally, we got a force vertically, and then we resolved the moments around this failure mode to be able to calculate exactly what the P magnitude of P is the unknown. It has a known lever arm length, but we don't know what P is, but we know what the others are. So that's what we did. A second way to do the same problem would be to draw a free body diagram that looks like this, that includes the whole gate, but also includes the water that sits above it. And if we did that, then we'd have to look at the forces that are applied on this free body. And that's a bit like the curved surfaces we just did, right? So it has a pressure acting on the top. The pressure acting here is going to be the height of this centroid below the surface times the unit weight of water times the area. The force acting horizontally would be the height of this centroid, which is halfway down this, acting on the side, multiplied by unit weight times this area, which is FH. And we'd have to include the magnitude of the weight that's acting downwards. And of course, just like before, this weight will act at a location which is given by the center of gravity of this location, right? It'll act through this point here, right? And so if we have that, then we can calculate this force times this lever arm, this force times this lever arm, and this weight times this lever arm have to equal this length times this. And the only unknown is P. So that's another way to do it. And the third way to do it is to draw our control volume, which goes right the way up to the surface. And so you can argue whether these are more efficient or not. And so this free body would have no pressure on the top because it's atmospheric, would have a linear varying pressure on the side, and so the magnitude of this horizontal force would be calculated again from this using the centroid, which is half the distance down here, but its point of action, y sub c, is going to be a third of the way down, right? 2/3 of the way down. If this is h. If this was h, then we know from the standard result, from a triangular distribution, the balance point for a triangle, if I folded this into one of these into a triangle, which I'm not very good at doing, then the balance point of this triangle would be a third of the way from this end, 2/3 of the way from this end. So it's sitting like this on this, 2/3 down. So this is it's kind of confusing. It's really the center of gravity of this pressure distribution is physically what it is. And so as a standard result, the balance point of that is a third of the way down. And so you know the point of action. So here you'd resolve moments. This force multiplied by this lever arm this weight multiplied by this lever arm, and this pressure multiplied by this lever arm. I guess that would be the shortest equation to use, right? And you'd have to do it relative to the failure mode. And so these are the three steps and to solve this problem. You can calculate any of the pressure distributions as an equivalent force by knowing where the depth of the centroid is and the properties of the fluids and its area. You can calculate the location where it acts, which is different from this, which is the slope distance from the surface along that plane, and it's from the slope distance to the centroid plus a small amount given by this standard result. For certain simple distributions, like a triangular distribution, there's a very simple location, which is 2/3 of the height down and 1/3 of the height up from the base. And if you have these pressure distributions or force distributions, you can always calculate some kind of failure of the structure, but for that you have to specifically choose the mode in which it's failing around. And so for this you have to take moments around this hinge, because that's how it's going to fail. You can't take moments around this and expect to get the right answer. You could take moments around any point here and find that it's in balance, but if it's a failure mode, you have to take the moments around that hinge. So those are the three steps that we talked about on Monday digitally, talked about on Wednesday in person, and reiterate today. Those are kind of the three steps. So that is all I want to say about that. And what else? We're going to talk about, don't talk about that, don't talk about that. Another example, just a quick example. Concepts rather than anything else. Then we'll talk about buoyancy. So what's the forces acting on this structure? And so you have oil. I guess you're unlikely to have oil with a 3-foot radius, 6-foot diameter buoy sitting in the water. But anyway, given that that's the case, what would the forces acting on this be? So one way to solve this, if you want to calculate the horizontal forces, is to realize what the pressures are that are acting on this. And so what you could do is you could isolate this with a free body, and the free body that they've isolated it with below looks like this. That's kind of funky. It puts a magnifying glass on it. So you isolate this, and you look at the magnitudes of the forces that are acting on this. And you know that the pressure acting on this is going to look like that. And you might be interested to calculate the behavior from that, or you might want to just calculate it from our standard result. It's easier probably to get it from the standard result. The standard result would be, if I draw the actual shape of the gate, so it would be like this. HC, actually it's equal to YC as well now. So F1 is equal to unit weight multiplied by the area times times HC times the area. First two terms are just the average pressure. What's the pressure distribution acting on here? Well, it's a tricky problem, I guess, in that if you think about it, what we said is that if you go from any point at the same elevation, dP dx is equal to 0, which means that if you go from this point here all the way to this point here, the pressures have to be the same. And you know that the pressure at this point on the left-hand side has to be equal to this. And so the pressure, by definition, at this point here, has to be equal to this magnitude here. And I guess also the pressure at this point here, if you go from here to here, I want to draw a straight line. If you go from this point to this point to this point, these pressures all have to be equal. And so the pressure distribution on this side is equal to this. And so if you want to do the behavior for this, then you have to be able to calculate the magnitudes of the forces acting on A, which would be equal to, well, I would do it by just calculating what the areas under the be the same as this. And so the average pressure the average pressure here would be, well, what's it going to be? If this is HC, the average pressure here is going to be F pressure at A is equal to HC multiplied by unit weight. The pressure at the base is equal to 2hc times the unit weight. And the average pressure is going to be the sum of those two divided by 2. The pressure average is equal to PA, this is kind of a convoluted way of doing it, divided by 2, which is B equal to HC plus 2HC over 2 times unit weight of oil, I guess. And so so this would be the pressure. So the force at A would be equal to the pressure at A times the area of A. And the area of A has to be actually H sub C. No. P average times A sub C, which is HC times the length into the page. Don't know what that is. Times length, whatever this length is here. So I don't think I did a very good job on that, and they solve it slightly differently, but that's the way to solve it. I guess the only important thing about the problem is that this is not zero. I mean, that's the trick to realize that. And it's not zero because you realize that the pressure here has to be the same at this elevation at both places. The pressure here has to be the same at both of these places. And if you resolve horizontally, you don't care about these individual forces due to these weights because you're only resolving horizontally, and they have no component that act vertically because you've isolated them. So, yeah, so I didn't do a very good job on that, but anyway. So the final thing that we might talk about is to talk about buoyancy, and maybe just go back to write something down. So the other parameter that we'll deal with is buoyancy. And it really comes from us being able to understand a bit about what we've talked about so far. And so if we talk about pressure versus depth, we've drawn these figures before. And let's call this H rather than Z because we're going down. And if we go down, this is pressure is equal to the unit weight times H. H is vertically downwards. And so if this is the surface of the liquid, and if we have a bucket that's below here, then what we know is that if we go across here, between H1 and H2, we know that the pressure acting here is this amount. And so we could imagine that we have a pressure acting on the surface, which is P1 equals H1 gamma. We know that we have a pressure acting here, which is equal to P2. And P2 is just equal to H2 gamma. And it would be equal to this amount here, right? And we know that we have a force acting downwards, which is W. And W would be equal to H2 minus H1 times an area. I like doing that. Multiplied by the unit weight. And so we know that this bucket, as we think, is kind of in equilibrium. And so if we remove, if we do a free body diagram, then P2 times A, acting upwards, has to be equal to W plus P1A. And so in this case, we can write P2 minus P1 times A equals W. And if we populate this with all these components, this is going to be A times H2 minus H1 times unit weight. And this is going to be area times H2 minus H1 times unit weight. So both sides are equivalent. And so what this is really saying is that the weight that is in here is exactly balanced by a larger pressure acting up than pressure acting down. And so that means it's in equilibrium because this expression here, of course, is derived from dP dz equals minus gamma. And if you recall, this is directly derived from F equals ma, where accelerations are 0. And so this is just a statement that the sum of the forces are equal to 0. If you take this away, then to hold this in place, you need an equivalent force acting downwards, which is equivalent to this. So the buoyant force that's acting downwards is exactly what this is, and it's always this. The buoyant force is just equal to, as you know, Archimedes' principle, the unit weight of the fluid that's displaced, the water that's taken out of this bucket, multiplied by its volume. And so that's merely where it comes from. It's just a force balance like we've had for the other components in this class, right? So that's the buoyant force. And so we can use that in the same way to calculate what forces would be on structures. This is a derivation here. Yeah, same derivation, don't need it. And you can solve for simple structures. And simple structures, this is kind of the same bucket diagram we had, right? We had a bucket with a pressure on the top, a pressure on the bottom, which was bigger. The sides would also have a pressure acting horizontally, but those wouldn't count if we're only resolving vertically. If we have a buoy or a buoy, a spherical buoy, then you can imagine that the pressure acting on it is perpendicular to the surface everywhere. And so it'd look like this collar, if you like. The pressure at the bottom would be larger than the pressure at the top. But this pressure distribution would be manifest as a buoyant force, which is just equal to the unit weight of the displaced fluid that isn't in the buoy, the evacuated buoy, multiplied by its volume. Always the case. And so that allows you to, for instance, calculate, again, free bodies to say what tension you need in a cable to anchor the buoy at a particular location, just by doing a free body. So in this particular case, you have a tension pulling it down. You have the weight of the buoy itself. It has the plastic orange buoy has some kind of weight to it, and a buoyant force acting upwards. And you can just resolve those forces acting upwards. Acting downwards, so the sum of forces is just equal to this. T acting downwards, W acting downwards, and the buoyant force acting upwards. If you know the volume of the buoy, if you know the unit weight that it's displacing, water in this case, seawater I guess, not 9.81 but 10.1. And if you know the weight of the buoy, if you're given it here, then you know everything to be able to calculate the one unknown, which is the tension. And just resolve it. So that's it. And so that's an easy enough thing to do. You know, we've talked about balloons as well. So a balloon is just sitting. We talked about how they work. And we rationalized the fact that really if you take a free body around the balloon, it's a bit different, isn't it? So you know that the pressure acting on the balloon from the atmosphere is some amount. The pressure acting on the bottom of the balloon probably doesn't change very much and is roughly the same amount. And so the only way that you can get a balloon to work is by making this density inside lower so that the weight of this mass, as it was in the bucket underwater, right? We took the water out of the underwater cylinder, and because the water was no longer there, it didn't have the balancing weight to keep it in place. Here we want to remove some of the gas that's in here to make it buoyant so that the density in the balloon is less than the density in the air. So rho B is less than the density in the air. And so we talked about the only ways we can do that is to, for instance, use the ideal gas law. P equals rho RT. Rearrange it in terms of density is equal to pressure divided by the gas constant for the whatever the gas is, multiplied by its absolute temperature of the balloon. So this would be the balloon. And so what we could do is we want to reduce the density. So we could either reduce the pressure. In a hot air balloon, you can't do that. It'll collapse. So that's not a viable one. Or you could replace this with helium. So you could either reduce this or you could increase the gas constant by changing the gas, or you could heat it up by changing its temperature and therefore changing the density. So that's the rationale for a hot air balloon, just for a different material. And I guess the other things to close out on this are stability. So if you think about a submarine in the subsurface, if you take the submarine and you somehow balance it on a pin inside the submarine, the point at which it balances on is the center of mass, the center of weight of that submarine being held in the air. And so that would be, I guess if it was this, it would be the midpoint of this piece of paper, right? If this was the section of the submarine. And so the weight of the submarine acts through the center of gravity. The buoyant force acts through the center of buoyancy, lowercase c here. So if the center of buoyancy is above the center of mass, then the center of buoyancy is kind of the buoyant force acting there, and you can think of the weight of the submarine as hanging off that. If it's below it, it will always be stable because it's like holding something on a piece of string. If you try and hold it where the center of gravity is above the buoyant force, then it's unstable. And so the equivalent of that is if the center of gravity is above the center of buoyancy, the idea is if you put the submarine off kilter by a small amount, there's a net moment which, if it goes further to the left, will grow and grow and grow, and it'll go until it turns upside down. And so I guess this is the principle of having a keel in a sailing boat, in that you have a center of gravity which is low, keeps the boat upright, you can have big forces acting on the sails and also the buoyant force acting on the boat, and it will always be stable. The converse is that it's unstable. It's easiest if the whole body is submerged, because the center of buoyancy will always be the center of that submerged shape, which doesn't change. If the shape is resting on the surface, then the center of buoyancy is the centroid of the removed volume of fluid, not relative to the shape of the boat itself. And so the center of buoyancy would be the centroid of this area here. And so as the boat rocks in the water, so that red outline, if you cut that out on a piece of paper and put it on your finger, the point that would be the center of buoyancy would be the centroid of that area. And so the difficulty for a floating boat is that the location of where the buoyant force acts change with the attitude of the boat. So that's just a point of note. And of course, you can do the same thing. The keel on a boat has if the center of gravity is above the center of buoyancy, then you have the same thing occurring as you have in this. It's just that in this case, the center of buoyancy would actually change because the shape of the boat is changing. Yeah. More complicated than we need for this class. And one example, we won't get through it, we've got a couple of minutes, maybe just say something about it. This question is asking if you have a plate that's held down by a weight that is submerged in water, what pressure do you have to apply on this plate before this lifts up? And I guess you just need to realize that if you're applying a pressure on this plate, it would look like this. So this is the pressure of air. So the force would be equal to the pressure of air times the area. And so if you increase the pressure of air, that force will increase. What's going to happen to the weight of this? Well, you'd kind of think intuitively that if you're putting the pressure on this, that you're also putting the pressure on this surface, and that should affect this. But it really doesn't. Because if you think about it, the reason that this has a buoyant force is because there's a pressure acting on the top here, which is less than the pressure acting on the bottom. And the buoyant force acting upwards is really compensating from that difference. But if you add a pressure on the top of this, you'll increase this force by some amount, but you also increase this one by the same amount. And so the difference between these pressures acting on the bottom will both increase, will not change, because the upper pressure will increase, the lower pressure will increase at the same rate, and so the net change in that won't change. And so that's how you can rationalize it. Certainly if you increase both these forces, it will change the pressure acting on this surface here, but the buoyant force, which is all that's pulling this down, is the same. And the buoyant force will just be equal to the unit weight of the displaced fluid, water in this case, multiplied by the volume of the brick. It doesn't change. And so if you go through this, you can just see that that's the free body. the weight of the brick, the pressure acting in this cavity multiplied by the area of the plate, and the buoyant force also acting upwards. So the net force on this is controlled by this. And the only thing you don't know is this, and you can solve for everything else. Sorry. Yeah, you know this is the area. So the only pressure you don't know is this. You solve for the pressure as a function of a known weight of the brick and the known displaced volume of water and its density. Solve for pressure. If you know what the pressure is, then you know what PA is. It's a gas, so you know that PA is also acting here. So you can write the manometer equation, that is PA minus, if this is Hg, hopefully I've got my signs right this time, times the unit weight of mercury. P atmos. And if we're taking gauge pressure as 0, this is 0. So you know what the pressure is, you know what the unit weight of mercury is, so you can calculate a height, and they're actually asking for delta H, and it's just the sine of that height. So you have the solution there. So anyway, we're at the witching hour. So that's it for fluid statics. As I mentioned, classes are online next week. The one class that's in this batch of fluid statics is 4.1, which is talking about accelerating fluids which are nominally static. And then after that, we'll start talking about moving fluids, which is Bernoulli equation. So we'll move from that. Homework for homework number 3, I guess, now is live. So you have the material for it. Thanks very much. Great.